Well, good morning. This is Tuesday, the 24th of October, 2017, 11 o'clock in the morning. It's supposed to be time for a linear algebra class. And right now, I'm the only one in the room, unfortunately. So I hope others will be arriving sooner rather than later. Okay? So let's get going from the current slide, which is a blank slide. Okay, here we go. Okay, we had started last time on 3.1. Chapter 3 is determinants, and 3.1 is determining the determinants of a matrix. And we had just introduced the concepts of minors and cofactors, and they have names, and the names mean something, but in reality, it's so much easier to just do it. And who cares what you call the things, just make sure you do it right. So it says, example 2 says, find all the minors and cofactors of this matrix A. So let me get my pen activated here. Let me just make a couple of announcements I probably should have first. The first one is super critical. It's just an announcement I saw posted on several places on campus. Friday at 10 o'clock, I believe it is I believe it's a UAB production of The Taming of the Shrew. That's one of William Shakespeare's famous comedies. It's the way he wrote it. There was a very strong-minded woman who refused to be subjected to a husband, and a very strong-minded husband who was going to subject her to his will. And Shakespeare had a lot of fun with that situation, The Taming of the Shrew. Well, evidently the UAB theater company, or whoever they're using, has decided to turn things around and have the man being the strong-willed person who is not going to be conquered, and the woman is the one trying to conquer him. And supposedly they claim it's just as funny, and Shakespeare is known for his play on words and puns and all types of inventions like that, and supposedly this has all of the good Shakespearean stuff, plus their bend on it too, making it a little more modern. So, Friday, 10 o'clock, Birmingham East Campus, the A.G. Gaston Auditorium. All right, the other thing that I would love to request of you, though I have a feeling neither one of you can do it, if either of you are still going to be around next fall, okay, here at Lawson State next fall, consider being on the math team. I know Jasmine was this year, but what we're trying to do this year, Mr. Racy, the coach, is trying to not wait until the beginning of fall term and then try to pull together a team in just a few weeks and not have many practice sessions and try to do something at the tournament. The time to do the preparations are now, getting ready for next fall. So if you're going to be around next fall and would participate, please let Ms. Geraci know. Her email address is ngeraci, that's spelled Jaraysy, at lawsonstate.edu. ngeraci at lawsonstate.edu. It's njaraysy at lawsonstate.edu. So, she really wants to identify people early, get started with practicing early. I think she said she was going to plan to practice on Fridays, and she'll do every other week on the Birmingham and every other week on Bessemer if that suits people better. I can help with practicing on Monday and Wednesday afternoons from 3:15 to 5:15, Tuesday, Thursday afternoon from 1:15 to 3:15, or anytime Friday morning on the Birmingham campus. So, but the other times are here on Bessemer. All right, those are the major announcements I know about for now. Let's get back to linear algebra. Okay, matrix A is 0, 2, 1, 3, negative 1, 2, 4, 0, 1. Okay? It says find all the minors and the cofactors of that matrix. Well, let's start with the minors. Okay? M11, for instance. You basically block out row 1 and column 1. The minor there is then what's left. M11 is negative 1, 2, 0, 1. Now, I don't know if that's what they're meaning. No, they mean go on and do it. Determinant of that, and that would be negative 1 minus 0. So that would be negative 1. Okay, M12 would be block out column 2. Sorry, I hit the wrong key. I had to wait for it to come back. Okay, that's the key I meant to hit. M12 would be wipe out first row, second column. Well, there we go. And your minor would be the determinant of 3, 2, 4, 1, which would be 3 minus 8 is negative 5. Okay? M13 would be block out the first row, the third column. Third column. Yuck! The pen isn't coming back. There we go. Okay? So M13 would be the determinant of 3, negative 1, 4, 0. Which would be 4. Okay? M21 is blank out the, I've just lost my entry there. Go back and get it. That was a 1. Alright. M21 is blank out the second row and the first column and the determinant of 2, 1, 0, 1, which would be 2. And then M22 would be come up here. Okay. All right. Sorry, my throat's going on me. Wipe out the second row, which we already have there, but now the second column, and the minor would be the determinant of 0, 1, 4, 1, which anyway when you do that, 0 minus 4, negative 4. Okay. Sorry, my head is getting so clogged up. Again, it's getting quite cold in the classroom. I think that's part of it. But I'm really having difficulty breathing. 2, 3. So wipe out second row, which we already have done. And this time wipe out the third column. Okay. And that's the determinant of what's left. 0, 2, 4, 0, which would be negative 8. And finally, 2, 3, well, that is 2, 3. 3,1, the minor 3,1 would okay. Okay. Getting these things to wipe out neatly and cleanly. Wipe out third row, first column. And it's 2, 1, negative 1, 2. Okay. 2, 1, negative 1, 2. And that determinant would be 4 minus a minus 1, so 4 plus 1 is 5. Okay. Now, I just don't have any room to do any more, but you can do them M3, 2, wipe out third row, second column, it'd be 0 minus 3, so negative 3. And then 3, that would be 3, 2, 3, 3 would be wipe out third row, third column, and what you have left is a 0 minus 6, so it'd be a negative 6. Okay. Brr. Now, that was the minors. What are the cofactors? The cofactors are the minors with either a plus or a minus 1 in front. And if the sum of your indices is even, it's a plus. If it are odd, it's a minus. Okay? The easier way is just like I showed you before, just to set up your grid and do plus, minus, plus, minus, plus. You know, that always works. So, the cofactor, I think they call it capital C 1, 1, because that's a positive position, it's going to be negative 1. M1, 2 is a negative position, so since the minor was negative 5, the cofactor is going to be positive 5. 1, 3 is an odd cofactor. M13 is an even, is a positive cofactor because 3 and 1 is 4, that's an even number, so therefore it's going to be positive. So since the minor was 4, the cofactor is also going to be 4. M21, on the other hand, being an odd cofactor, you're going to change the sign of that. So M21 was 2, so C21 would be negative 2. So you go on like this. Every other one, you change the sign, and every one you don't. If it's sum is even, you don't change the sign. So M22 would be minus 4. M23 would be positive 8. M31 would be negative, that would be positive 5. Okay? So continue like that. So let's see how the book did. M11 was negative 1, M12 is negative 5, M13 is 4, M121 is 2, M22 is negative 4, M23 is negative 8, and M23 is negative 8, and M31 is positive 5. Now, cofactors, exactly the same digits, and when the subscripts are even, it's exactly the same number, same sign. So C11 would be negative 1, C12 would be positive 5, C13 would be 4, C21 would be -2. C32 okay, I've lost I can't remember which one I left off with. C22 would be -4, C23 would be +8, C31 would be 5, and then C32 would be +3, and C33 would be -6. All right. Now, with that then under our belt, I don't know if anyone's coming today or not, but I need to go get something to clear my head. So I'll be right back. I'm just going to pause this for All right, sorry about the delay. I'm not sure I'm much clearer talking, but at least I feel a little bit clearer, so sorry about that. So, what we were getting ready to do was the determinant of a square matrix. And let me clear the ink off of this slide. The definition below is called inductive because it uses the determinant of a square matrix of order n-1 to define the determinant of the matrix of order n. Excuse me. So here's the definition of the determinant of a square matrix of any size, n. Okay? If A is a square matrix of order n greater than or equal to 2, so A is a square matrix of order n greater than or equal to 2, that's what's given, then the determinant, okay, that's going to be what I use for that, of A, which you could also do bars around the A, they look like absolute value bars, but they're not, is the sum of the entries of the first row of A multiplied by their respective cofactors. Okay? Is the sum of the entries in the first row of A, and I'm going to tell you right now, it doesn't have to be the first row. Any row or any column, the sum of the entries of any row or column of A multiplied by their respective cofactors. Sorry about the writing here. This is such an awkward little screen to try to write on. Okay? So here's how you say that. The determinant of A is equal to the sum from j equal 1 to n. N is the size of the matrix. And it would be Aij. Well, they're saying A1j. So I'll put that for 1j. That means first row. They're just going to do first row. But it can be any one of those for any I. Either Aij or Aji. It doesn't matter. Times C1, in this case, J1. Wow, my ears just cleared enough. I feel better, but I'm not sure it's a lot better. So that is A11, C11, plus A12, C12, plus A13, C13, plus ... all the way up to A1, n minus 1, c1 n minus 1, and so on, plus up to n, plus a1n c1n. Okay. Now that's just with 1. It can be any I there. The I doesn't change, and it can be either row or column. Okay. When you use that definition to evaluate a determinant, you are expanding the cofactors of the first row. Okay? Now, it doesn't have to be the first row. Any row, any column, you just go from there. So let's do an example, and we'll use the first row this time. So let me erase all the ink on the slide and find the determinant of this matrix A. I believe we've seen it before. 0, 2, 1, 3, negative 1, 2, and 4, 0, 1. Now, you can use first column, row. You could use first column. You could use the third row. You could use the second column. It doesn't matter which one you use. Now notice I picked out those 4 particularly because those are 4 that have zeros in them. So usually if I'm trying to do the determinant of a big matrix that's anything larger than a 2 by 2, and they all have to be square, remember that, I try to find the row or the column with the most number of zeros in it. Makes life a little bit easier. So since they're illustrating it with the first row, we'll use the first row. So this will be 0 times the determinant of minus 1, 2, 0, 1. Okay? Well, that's going to be 0. It doesn't really matter. Okay? Now, going down the first row, now, here's how I like to do it, and this is how I do it. It's doing the same way they did, but rather than saying plus 2, because I know that position is a negative position, I'm going to do minus 2 times the determinant of what's left when you cross out row and column. That's 3, 2, 4, 1. Okay, and then plus 1, because that's a positive position there, and the determinant that's left over would be 3, negative 1, 4, 0. Okay, and then it's easy enough to do those 2 by 2s. First is 0 altogether. So that would be a minus 2 times a 3 minus 8. That would be a minus 5. Minus 2 times minus 5 is positive 10. Plus 1 times 0 minus a minus 4. That's plus 4. That's 14. So there's the determinant of that matrix. Okay? Make sure I did it right. I did. Let's just for funsies do the first column instead. 0 times what's left over, that's still 0. Minus 3 times 2 minus 0, so that would be minus 6. And plus 4 times 4 plus 1 is 5, so plus 20. And that's also 14. Okay? Let's do the third row and see what we get. It's a positive 4 times 4 plus 1 is 5, so that's 20. Okay? Plus 0 plus 1 times a minus 6, so that would be 20 minus 6 is equal to 14. Let's do the second column. That's a minus 2 times the determinant that's left over. That would be 3 minus an 8. That would be a minus 5. Minus 2 times minus 5 is plus 10. Then a minus 1. It's a positive position, but a minus number there. So it would be a minus 1 times 0 minus 4, or minus 0, that would be a minus 4 So that would be minus 1 times minus 4 is plus 4. And that would be 10 plus 4 is 14. Okay, now I did the short and easy ones because I picked the ones with zeros. But see, it doesn't matter which row or which column you choose. Just be consistent. Be careful. Keep up with your signs, both the positional signs and the crisscross signs, you know. They can reach out and bite you, but be careful with that. Okay, and we got 14. They did second row expansion and first column expansion. We did first column, we didn't do second row. Let's do second row. We'll go across this way. It's a minus 3 times the determinant of what's left. That would be a 2 minus 0, so that would be minus 6. All right, I'm so glad you're here. I get so bored talking to myself. But I'm glad to see you anyway. Hopefully I've already taken my 2 breaks to go clear my head. No, 1 break, sorry. Because I just got so I could hardly breathe. But I did go drink some Coke, and that fizzing, I guess, helped loosening it up. I got some of it cleared. It's not all cleared, but at least I'm better than I was. Okay, let's swap the lights, turn on the projector, so that you can see what I'm doing. Goodness gracious, I'm cold. Okay. I saw the technician go into the room this morning. I should have told him, turn up our heat, because this room is just, it says it's 68. I can work outside in 68 and I don't feel this called for working. It's burning more calories. But anyway, what you see up here is we're defining the determinant of a matrix. And I had already done several. You can go back and listen to those. What I think I'll do now is clear this so it won't be so messy for you to see, and hopefully you'll see what's going on. So I had gotten really sloppy in it. Because no one is in here to have to watch it. I figured if you were at home, you could go back and see it as many times as you needed to. Okay. Their definition specifically said first row, but then later they said any row, any column. Okay? So here's how you do the determinant of a matrix. Now, I wanted to remind you of what we're doing here. The book uses the terms minors and cofactors, and it's all well and good. But if you follow just the simple rules, you can take all that into account without having to give it names, okay? So I'm going to show you what I feel like is an easier way. So what we're going to do, we want to define the determinant of A. So determinant of A, that's what A is. So the determinant of A, that should be a straight line there, okay? Now, you can do it any row, any column, okay? It showed you the second one, so I'm going to do the second. I had already done the first row, the first column, the third row, and the second column. I did those because they had zeros in them, and that makes it easier to do. But now they're going to do the second row, and it still should work, even though we don't have any zeros to make it shorter. Now I think what I'll do is down here. I'm going to start with the second row and go across the second row. So the first entry on the second row is a 3, right? Except that it is, from your cofactor idea, it's in a negative position. Remember? Always start with a plus. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Or plus, minus, plus, minus, plus, minus, plus, minus, plus. However you do this, plus, minus, 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 minus. However you get there, as long as you go horizontally or vertically, it always is going to be a minus position, okay? Or you can say that's the 2, 1 position, that's an odd number, negative 1 raised to odd number is minus. After a while, you just look at it and know that's a minus position. So we're going to start with a minus 3, okay, and then multiply that times the determinant that's left over when you wipe out that column row. This then gives you your minor. And that determinant is 2, 1, 0, 1, right? Okay. Next, we'll go to the second entry on the second row, okay? And this time, that entry is a minus 1. It's in a positive position, plus, minus, plus, you know, but it's a negative number. So that would then be negative 1 times the minor left over here. That would be a 0, 1, 4, 1. Right? Okay? And then the final entry there is a 2, but it's in a negative position, right? Okay. Okay. We're going to do this one. That 2 is in a negative position, plus, minus, plus, minus. So that would be a minus 2 times its determinant left over, 0, 2, 4, 0. Okay? Now, 2 by 2s are pretty easy to do. A minus 3 times this determinant would be 2 minus 0. So that's 2, right? Okay. Minus 1 times, that would be 0 minus 4, right? So that would be a minus 4. Okay. Minus 2 times 0 minus 8, right? So it would be a minus 8, negative 8. So this will be a 6 plus 4 plus 16, right? It's a minus 6. I don't know where the minus sign went. Minus 6 plus 4 plus 16. Okay? Well, this is 20 minus 4 minus 6 is 14. And that's what we got. Every other way we did it, we always got 14. And you will. There's no way around it. That's how you do the determinant. So it doesn't matter which row, which column you choose. They start with the number, then deal with the cofactor, which is a sign with the minor. To me, attach the sign, because the sign is positional. All right, we got perfect attendance today. Good to see. Okay? And by the way, I may not have said this to you, but we're on page 106. It's chapter 3, determinants, and the section 3.1, determinant of a matrix. And we're doing example 3. And I had already determined the determinant 4 different ways. They did one more way, so I just finished the 5th way. You could do it 9 different ways. Each of those columns in each row, you could do your determinant that way. All right. Now, right at the bottom of the page, it says the following theorem states what we've just been talking about is known as Laplace's expansion of a determinant after the French mathematician Pierre-Simon de Laplace. Okay? And by the way, he lived, I don't know if Newton had died yet or not. Newton, I think, lived in the early part of the 1700s. I don't remember how late he lived into it. But Laplace was a little later than Newton, okay? In my memory, I don't know. The old gray cells, they don't always work. So let's do theorem 3.1, since not all of you have books here to look at it. And my writing stinks, especially on this little bitty patch that I have to write on here. This is expansion by cofactors. Let A be a square matrix, okay, of order n, okay. Now usually we let the n be greater than 2, greater than or equal to 2, okay. Then the determinant of A, is given by the summation j equal 1 to n, whatever the size of that matrix is, A sub ij, C sub ij, which would be A sub I1, C I1 plus A I2, C I2 plus dot 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 all the way up to and including C I N, I'm sorry, A I N, C I N. Okay? Now, the J's are, no. Yeah, that's right. Yeah. Or, you can do the summation. This time they're going to do the i's equal 1 to n of A ij, C ij, which would then be A I1, C I1 plus A I2, C I2 plus dot 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 all the way up to A I N, C I N. Now, that's using the definition of cofactors. I don't find that the easiest way to do it, but that is, if you like cofactors, this is it. Okay? This is saying whether you're using one row or one column, doesn't matter. Whichever you use, you can go across that row or down that column, multiplying the entry by the cofactor of that entry. Okay? Again, I'll do another one. And when expanding, this is what I told you before, by cofactors, you do not need to find cofactors of 0 entries because the 0 times the cofactor is 0. So you don't even have to worry about it. Okay? So let's do a 4 by 4. Okay? Can I erase this? All right, Pig? All right. Here is matrix A. Big old hairy matrix. 1, negative 2, 3, 0. 1, negative 2, 3, 0. Negative 1, 1, 0, 2. Zero, 2, 0, 3. Three, 4, 0, negative 2. All right, I think I did it right. Oh, man. Now my eyes are dry and itchy. I don't know. I'm freezing in here. I like to sit here with my hands right here because the fan from the computer is blowing out there. It's a little bit of warm air, but I can't write that way. Okay. Now, remember basically what Laplace's expansion says. You can pick any row, any column. Guess which is going to be the easiest one to pick? Yeah. No, I'd just say to find the determinant. Okay? The easiest one to go is that third column. Look at all the zeros in it. Zeros are so easy because you multiply something by zero, zero. You don't have to do the cofactors then or anything close to it, the minors or anything else. So what I'm going to do, the determinant of A then is going to be, you pick that first, you're going to use the third column. So I'm just going to draw that line through it right now because that's what we're going to use. Okay? And we're going to start with the 3 here. Well, the first thing I do, this is where I deviate a little bit from that. I look at the position of that 3. And is that a positive position or a negative position? Positive. Plus minus plus. Okay? That is a plus position, so we'll leave the sign the same. It is positive, so it'll be 3. And it's 3 times the determinant of what's left over from what we have there. Minus 1, 1, 2, 0, 2, 3, 3, 4, negative 2. Okay? And then the others are all zeros. So you don't have to write any more down. They're done. But you still got this one to do. Now, which would you choose to do on this one? And it really doesn't matter. 2 are very easy choices. What would you say? Guess what? Okay, first which? Row or column? Okay, you could. Column. First column because it has a 0 in it. Or the second row because it has a 0 in it. So either one of those will be fine. I don't care. Okay, which one you want? First column? I like that one too. Okay? So don't forget your 3. Okay? The 3's still there. We're going to do the first column, so I'm just going to go down this way. Now, that minus 1 is in what position? A positive or negative? It's a positive position. So we don't change the sign. We leave the sign the same, which happens to be negative.
Is that a Z3?
Say that again?
Is that a Z3?
D3. Oh no, this is an equal sign. I'm sorry, my pen drags. Okay. He's making fun of my writing. I can tell. I will remember that now. Okay. Okay. So that's going to be a positive position, so we leave the sign as is, which is a minus 1. And that's going to be by the remaining, when you wipe out the row and column, the remaining matrix, which is going to be what? 2, 3, 4, negative 2. Okay? Now, continue down the first column, because that's what Jasmine chose. So we'll continue down the first column. First column stays marked out, but we don't have to do anything to the second entry because this is 0. It's going to make everything 0. So we go on down to 3. Is that a plus or a minus position? Plus. So it's going to be plus 3. So that's going to be plus 3 times the determinant of what's left when you wipe out that row and column, and that's going to be a 1, 2, 2, 3. Okay? That's going to end my parentheses there. All right. So this is going to be a 3 times a negative 1 times And what's the determinant of that 2 by 2? What's the determinant of that 2 by 2? Negative 4 minus 8 are your downward diagonals. The main diagonals are positive. The upward diagonals are negative. So this one's negative 2 minus 8. I mean, negative 4 minus 8 is negative 12. So it'll be times a negative 12. Okay. Plus 3 times what? Three minus 4 is a minus 1. Okay? Okay. And the rest is pretty simple. That's going to be 3 times positive 12 minus 3. That's 3 times 9, which is 27. Okay? Let's see if I did it right. No. All right, I did a dumb mistake somewhere here. 3 times what's left over, minus 1, 1, 2, 0, 2, 3, and 3, 4, negative 2. How can I make the dumb errors? Okay, so it's 3 times the negative 1 times what's left over, which is, oh man! I don't know how I did that. This is a 3 right here, not a 2. The negative 1, that's a 3, 2, 3, 4, negative 2. And there I erase the 2 and put a 2. Okay? Let's erase the 2 and put a 3. All right. Now that one will be negative 4 minus 12 is negative 16. Well, let's see. Goodness gracious. All right. So that would be 3 times a 16. Minus 3, that's 3 times 13, and that is 39. And that's what they got. Sorry about that. Be careful, I don't know how I got that 3 from 2 over there. Just knock it there. As you see in matrices, all the operations are really pretty simple. Adding, multiplying, pretty simple numbers. But there's so many little steps, and sign changes and things like this, it's real easy to sneak up and make a silly mistake.
What was messed up there?
What's that?
I said, what was messed up there?
Well, I wrote when I did like that first row and first column here. This would be what I was right there. I put 2, 2, 4, negative 2. I put it. The 3 was here. I put a 2 there. And that's where I got it wrong. But it wasn't an operation. It was a copy. You know, I didn't multiply wrong or add wrong. I wrote it down wrong. Okay, and that never helps. Okay. All right, I'll leave that up as long as you need. What's that? This is 2.1, 3.1. 3.1. Okay. Now, if you haven't noticed yet, occasionally you'll hit some shortcuts. For instance, 2 by 2s is pretty easy to do. Just like doing the inverse of a 2 by 2 matrix, you use the determinant, right? And you flip some things around. So it's a pretty simple process. 2 by 2 finding determinants are real easy. Okay? 3 by 3s, however, that was a 4 by 4. There's not any easy ways to do a 4 by 4. But when you get down to a 3 by 3, there is another method to do it that you don't even have to keep up with the signs, really. Okay? Or with all the parentheses, really. Okay? And I'll show you what it is. Okay? It's just a technique that works, but it only works for 3 by 3s. Okay? Man, I can sit with my hand in front of this fan. Ooh, it feels good. Okay. Here's an alternative method commonly used to evaluate the determinant of a 3 by 3 matrix. So write down your 3 by 3 matrix. A11, A12, A13, A21, A22, A23, and A31, A32, A33. And you're trying to find the determinant of it. Okay? Here's the technique. Write down the first two columns again. A11, A12, A21, A22, A31, A32. Okay? It looks kind of nuts, doesn't it? But here's what you do. On your downward diagonals, just multiply them together. Right? And those are always positive, what this is. Then add the product of those. And add the product of those. Okay? Then you do your upward diagonals. Minus the product of those, minus the product of those, minus the product of those. 3 additions, 6 multiplications. No, yeah, 1, 2, 3, 4, 5, 6. 6 multiplications. You add 3 of them, subtract 3 of them. And you got it not. And you don't have to crisscross, mark out, or anything else. Just go down your diagonals in the positive way, up your diagonals in the negative way. Okay? So, I think we're going back to one we've already done. Example 5. I think I can leave this up here. Okay? Here's example 5. A is this 3 by 3 matrix. 0, 2, 1. 3, negative 1, 2. 4, negative 4, 1. Maybe we haven't done this one. That doesn't quite seem right. Okay? Now, to get the determinant, what I'm going to do is first erase the brackets here. I'll leave that one if you want to. Okay, next thing I'm going to do is copy those first 2 columns again. 0, 2, 3, negative 1, and 4, negative 4. Okay? Now, I'm going to do the determinant of A by going down the diagonals and then minus up the diagonals. So this diagonal, guess what that is? 0. Nice, huh? Plus, what's the product there?
8.
Second?
8.
Not sum, product. 2 times 2.
It's 4 times. All times 4 is 16.
16. So that would be 16. And then that one?
Negative 12.
Negative 12. Now, it doesn't mean they're all positives. You just add them together, okay? Now you do your negative, your up ones, okay? And what's the first up one there?
That is a negative 4.
Yeah, negative, a negative 4 would be plus 4, okay? The next up one is, guess what?
0.
0. And the next up one is
negatives. I mean,
Yeah, it is a positive 6, but because you're up it, it's a negative 6. Okay? Now, let's add our positives. That would be 20 minus 18 equals 2. I sure hope I got it right. Yay! I got it right that time. All right. I found that much easier than having to keep up with all the crisscrosses and everything else. Got it? Or question? Okay. Later, we're going to do a cross product of vectors in 3 space, and we're going to use this technique for that as well. We're going to use the determinant. And it happens to work very, very nicely. Okay? Not there yet, but we can do it. Okay. Now, there is a little blurb, linear algebra applied. The diagonal process illustrated in example 5 is valid only for matrices of order 3. For a higher matrix, you must use another method. Sorry, we'd already said that. Linear algebra applied. If x, y, and z are continuous functions of u, v, and w, the continuous first partial derivatives, with continuous first partial derivatives, then the Jacobians, juv, juvw, are defined as the determinants. Now, time out. Jasmine is taking Cal 3 now, right? We haven't gotten to partials yet. Have you already had Cal 3 or have you had it? You have. So you've done partial derivatives. Partial derivatives are not that bad. They're pretty easy stretch from what a regular derivative is. Just got a couple of other things to do. But this is your definition of a Jacobian. Later we'll do some more things with it, but right now that's all you need to know. So you can look it up if you ever need it. Now, where did that get its name? I'm guessing someone whose last name was Jacob or Jacobia or something like that. That might be a good paper topic if you haven't chosen a paper topic yet. Who came up with the Jacobian? Okay. But that's for another day. Let's go back to our triangular matrices. Remember them? You only refer to these when they're square matrices. Remember? Square matrices. Okay? And an upper triangular matrix is going to look something like this. A11, A12, A13, ... A1n. Zero. A22, A23, ... A2n. Sorry, my throat's clogging up again. Pain in the neck. Next row would be 0, 0. A33, ... up to A3n. Then you go ... downward. And this is all zeros. Down here is zeros. Over here is zeros. Well, I didn't need it there. Down here is zeros. Over here are all zeros until you get to, A-N-N. And you got 3 dots down here and 3 dots everywhere. Okay. That's your upper triangular matrix. What are the characteristics of it? You have a main diagonal matrix. Okay? Everything below it is 0. everything above it could be any real number. Okay? So that's your upper triangular matrix. Similarly, your lower triangular matrix is going to have the same diagonal. Okay? So this is upper. Here's your lower. It's going to be A11, but then it's going to have zeros after that. Okay? A21, A22, and zeros after that. Okay? A31, A32, A33, and zeros after that. Dot, dot, dot this down to N1, N2, N3, dot, dot, dot to N, and then dot, 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 this on down, that on down, that on down, everything. Okay. Here, you have that same diagonal matrix that you had here, but now everything above it is zero and everything below it is not necessarily zero. So this is your lower triangular matrix, L. Okay? Now, a matrix that is both upper and lower triangular, obviously then, if it's upper triangular, it has zeros here, lower triangular, zeros there. If it's upper and lower, everything below is a zero, everything above is a zero, so all you've got is a diagonal. Okay? And therefore they call that a diagonal matrix. If all your upper elements above the diagonal are zero and all the lower elements below the diagonal are zero, the only non-zero entries in the matrix are your diagonal entries. Okay? Now, before we go to diagonals, though, let's talk about finding the determinant of a triangular matrix. And that turns out to be a very easy thing to do. Goodness, I'm hungry. I think that's the other thing that gets to my head. I think I get low on blood sugar and everything clogs up. So to find the determinant of a triangular matrix, whether it's upper or lower, simply form the product of the entries of the main diagonal matrix. I wish I had left those up there then. And I can't go back and reproduce. But if you think about it, well, let's do the one they have here. Here's A. 2, 3, -1. 0, -1, 2. 0, 0, 3. Okay? Now, if I were to say, find the determinant of that matrix, what would you do? You have really you have several choices. What would you choose? If I said find the determinant of that matrix, how would you proceed? Okay, say that again.
You hit two of the columns. Are you trying to find the determinant?
Yeah.
You hit like two of the columns.
Oh, okay. Pick either a column or a row.
Yeah.
Just one of either. Which one would you pick?
I'll pick 1 and 2.
Okay. You only pick
I'll
one.
pick one. Oh, yeah, just one.
A column or a row?
Yeah, one.
Which one?
One. Oh.
Row or column? First column, I agree with you. Let's go with first column. Okay? Now, what is the position for that 2? Positive or negative? Positive. So it's 2 times the wipe out that row, that column, the matrix here. That would be 1, a negative 1 times 3, be a negative 3 minus 0. So it's 2 times negative 3 is minus 6, right? Everything else is 0. Well, what did you just do? You just took the product of the diagonal. You didn't use these things up there at all, okay? Because you wiped out this row, so you didn't use those 2. These are just zeros, so you're not using those anyway. And this 0 basically wiped out that 2. So all you had was the product of the main diagonal. And for any triangular matrix, upper or lower, your determinant is the product of that main diagonal. Any one of those in the entries in the main diagonal 0, the determinant of that thing is 0. Okay? But if they're all non-zero, then the determinant is a non-zero number. Okay. All right. So that's theorem 3.2. If A is a triangular matrix, and of course that means it's a square matrix of order n, okay, meaning n columns, n rows, then its determinants is the product of the diagonal entries, of the entries of the main diagonals. That's it. In other words, the determinant of A is equal to A11 times A22 times A33 ... to ANN. Just the product of those main diagonals. Okay? Now, they do a little proof, a mathematical induction proof. We don't have time because it's time to end this. We'll begin next time on example 6. Let's see if we got, so close to finishing. So on this 3.1, you can do any of the odds 1 through 11. Number 11 is pretty interesting. You might want to try it. Either 13 or 15 or both. Do number 17 if you can. Do any of the odds 19 to 31. There's a whole passel of those. Okay? Do 33. Do either 35 or 37 or both. Either 39 or 41 or both. Okay, there is a true false there. You can look at 43 if you'd like. There's 3 different sub things there, so I'll let you read that and see what to do. Let's see. Well, you can stop there and we'll pick up the rest of those next time. All right. So we'll pick up example 6. That's all we've got to do in 3.1, and then we'll move on to 3.2. Yes?
I'm going out of town, so I could possibly miss the next 2 classes.
Okay. Did you get the second test?
Yes, sir.
You did. Both of you did. Chapter 2 test.
She wasn't here.
Oh, you don't? In fact, did either one of you get it? Let me just see.
I got a copy of it.
Okay. Okay. There's test 1. 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 I have a lot of copies of test 1. I've made out several different ones. Here's test 2. Ha! There it is. Okay. Good deal. Thank you. You did get tested.
Yes, sir.
All right. Good deal. We will see you Wednesday. Now, you think Wednesday may be gone or next week?
I could possibly make it.
Okay, well,
Thursday,
whatever.
Thursday I could.
I mean Thursday,
make
yeah.
it, but Tuesday I'm not sure.
Right, okay, well, whatever. But I'll record everything, and if you can. Now, I mentioned this earlier before either one of you came in. Mr. Racy is looking for math team. She wants to get the math team started right before the tournament or the competition. So therefore, what she's saying is let's get started now to start preparing for next fall. Are either one of you going to be here in the fall? Or both of you graduating before then?
Yeah, I'm graduating.
I figured you both were, because at this level you probably would be. Okay, we will, thanks for your participation this time. Did you find it okay? Yeah, good deal. Okay.